Hello, my name is Nick Orialis. I'm an instructor here at FSI, and my student Chelsey has been studying the physics of blood pattern analysis for the last 6 weeks.
Thank you. All right. So, my name is Chelsey. My mentor is John Arco, and I have been studying the bloodstain pattern analysis and the application of weapon identification. And I'm from Frontiers Science Institute. So, what is bloodstain pattern analysis, BPA? It is the analytical study of bloodstains and how they are formed. It's used through the use of physics, and we usually use the application of projectile motion and in second law motion. It can be used for the recreation of crime scenes, and investigators analyze bloodstains to find out a variety of things. This includes the origin of splatters, the size of attacker and victims, and many other applications, such as the number of assailants, number of strikes that could have been done, the position of the victim as well as the perpetrator, the wound infliction order, so which wounds were inflicted first, second, last, and the time of the crime, how dry the blood was, and the type of weapon and the size of weapon. The last two are the ones we will be looking at. So, the properties of bloodstains, the main property that is studied is velocity. And these include low velocity, which is the result of blood dripping from a weapon at rest. So after it has already gotten blood on it and someone is hanging it down by their side or whatever, blood is going to drip off of that weapon. And that's just such a low velocity that it's going to make about 4 millimeter to 8 millimeter in diameter blood droplets. And this also is the result from a wound. So if someone is stabbed and keeps walking, and as they're walking, it's going to drip onto the ground. These are usually less than or equal to 1.5 meters per second, so it's very low velocity and in speed. Medium velocity is the result of a blunt object hitting someone, so the blood spatter from that initial hit is usually medium velocity, and it's also the result of severed blood vessels. It usually is 1 millimeter to 4 millimeters in size and diameter, and it's a result of 1.5 to 30 meters per second in speed. High velocity is the result of gunshot. So when someone is shot, the blood spatter on the wall behind them is high velocity. This is usually less than 1 millimeter in diameter and is more than 30 meters per second. This is very fast. So, calculating bloodstain angle, a lot of analysts use this as it's called stringing, as you may have seen on Dexter. The stringing is they first find the angle of the blood droplet, and the way they do this is through trigonometry, and they use the SOHCAHTOA. So SOHCAHTOA, this is, sine, cosine, and tangent, and we use this formula, x equals arc sine width over length. So as you can see here, the blood droplet is traveling in a spherical shape, and as it impacts, it's going to have a certain width and a certain length. And that can be measured right away and then calculated to find the angle of impact. And then as soon as the angle of impact is found, they string is attached to the blood droplet and put it at the angle. And this is done with all the blood droplets in the spatter. And then eventually, you'll start to see the strings converge at one central point where they all intersect. And this is called the area of convergence. This is where the blood spatter originally happened, where the wound was, where the person was. And this is used for recreation of crime scenes, as we stated before. The next is weapon identification. As you can see here, this is Chelsey swinging a keyboard, and me swinging the mallet. And since weapons have many different varying sizes and striking surfaces being the surface that you strike someone with a weapon, and they cause different cast-offs. And what cast-offs are the trail of blood droplets that result from the backswing and As the blood accumulates on the object and you swing back for your backspin for the next hit, that blood is going to fling off your object and hit the ceiling or other surface. This is called cast off. This can be easily documented on paper as we did. So as you can see up here, this is cast off going this way. And see, as I swing back, the cast off is going to hit up here, and Genesis is going to hit up here. The physics of bloodstain. In cast-off bloodstain, we have varying velocities because of varying strength. Someone like me is not going to have as high strength as someone much bigger than me. So different velocities, mine's probably going to be more medium or low velocity, while someone much bigger could be high or medium velocity. And they're all mostly medium velocity. The elongation of droplets, so as you swing back, you're going to have the initial hit of blood droplets on the ceiling, and then you're going to have the ones that are back here. The ones that initially hit are going to be about 90 degrees, about like that, and then the ones that are going to hit farther back are going to be more 60 degrees to lower degrees, because you have a lower angle you're hitting at. And as you can see here, more elongation, the 10 degrees is much more elongated than, say, the 90 degrees. So as the degree gets smaller, the elongation is going to get bigger. And this can tell you what direction the cast-off would hit. And our hypothesis was if the size of the striking surface increases, then the width of the cast-off is going to increase. So if you have a higher striking surface, as say on this candlestick holder, you're going to have a wider cast-off when you swing it back, as say a crowbar. A crowbar with a striking surface that is much lower than the candlestick holder is going to have a much smaller cast-off when you swing backward. And as the length scale increases, the cast-off width is going to increase as well. Now, the weapons that we use are a variety. We didn't actually measure anything that has to do with the specific weapon themselves, but the size of their striking surface. So as you can see, these are really, where did I go? Okay. Okay, and as you can see, the length scale is the only difference here. So this is what mainly we are measuring in the actual weapons themselves. So the keyboard is going to have an 18-centimeter length scale as opposed to the metal pipe that's going to have a 3.5. So this is going to change the size of their cast-off. So first we had to make blood, since we could not use real blood. And the properties that we needed for this blood needed to be viscosity and density. Because we were not testing anything to do with composition of blood, these were the only properties that we needed. And the most accurate blood formula that we found was glycerin, the main ingredient in beauty products, and water. So 1 part glycerin, 2 parts water, and then food coloring until you got the color of blood. This is a sample of our blood. As you can tell, it's not as viscous as water. It's much more thick and viscous. I'll pass this around so you guys can see it. And that is a sample of the blood that we used. So first we had to test the accuracy of our blood itself. So we dropped it from varying heights and compared it to past experiments that had been done with real blood. So we dropped it from the first story in the stairwell, the second story in the stairwell, the third story. And as you can tell here, as your size gets bigger in height, your size and diameter of blood droplet is going to get bigger as well. So as we dropped it from varying heights, we were able to see the different impacts. And we also dropped it from varying angles, so we can see the correct elongation of each angle. The viscosity, to do this, we used a graduated cylinder, and we filled it with our fake blood and dropped a ball in it and timed how long it took to get to the bottom of the graduated cylinder. We then plugged this into the viscosity formula and found the viscosity of blood from other sources. During setup, we had to set up a laboratory space that would be big enough for the researchers to actually swing back all the way to get his full swing. This was an 8-foot by 2.5 feet area, and we set this up in a classroom in Bishop Blair, and we set up the stool in the middle, which had a latex glove on it. This latex glove was filled with our blood, as well as a strip of felt cloth. This felt cloth simulated tissue, because if we had just the regular glove, it would act more like a water balloon than actually tissue being hit with a weapon. So as we had the felt tissue, it absorbed more of that blood and acted more like tissue. The glove was put on a stool, and a small incision was put into it so that the air pressure was not unexact. And then the height of the researchers and the height of the stool was kept constant throughout all of the experiments as to not cause any more variables to be added. And the foot placement of the researcher was also kept constant. In experimentation, the researcher was given the weapon that had been measured, and the latex glove was hit 3 times so that we could see the cast off of each time. And the bloodstains were the result from the back swings, as we said before, and the documentation of cast-off is then analyzed and recorded. So in data collection, we collected all of the average width of the cast-off. So this included the initial, so right when it hits the ceiling, the halfway point between a meter and then the 1 meter. And as you can see, we have the same length scale as before, the size of the striking surface, and then the average cast-off width. These were then put onto a scatter plot, and the width of the cast-off was in relation to the size of the striking surface. So as the length scale on the x-axis increased, the width on the y-axis also increased. The correlation coefficient that we ended up coming to was 0.96. This means the best fit line that we had calculated was very close to what it would really be, and closer to 1 you are, the better it is. And our formula that was calculated was 1.42x minus 1.77. Here is our scatter plot and our best fit line. As you can see, all of our data points are almost exactly on that line. For discussion, we had the striking surface size can now be calculated through our formula. It could be estimated. We don't want to take this as an exact measurement of the striking surface, but it is definitely a very good reference to use. The size of the cast-off bloodstain can also be estimated, but you don't usually have just a weapon and no bloodstains at a crime scene. So you would be mainly looking for the crime scene weapon rather than the bloodstain. And why it works, the bigger the striking surface, the more area the blood is going to accumulate over. So as you swing back, the more area for the blood to fling off. And it flies off at different parts of the striking edge during the back swing. So this is the formula that we used again, and it can be changed to only use the width. So you do y plus 1.77 divided by 1.42, and that will give you the width of the size of your striking surface. Y being the width again, and x being the size of the weapon. So in conclusion, this formula can be used to calculate weapon size and can rule out suspects, locations, and even different kinds of weapons. The changing of the way the weapon identification truly is used in forensics now. So bloodstain analysis isn't really studied. In forensics, this is going to give a whole new idea to weapon identification. It's not completely accurate, as I said before, but it could be used as a great reference. From this point, accuracy of our formula can be tested, and then you can also differentiate between different swings, so initial swing, second swing, third swing, and sizes of attacker and victim can also be calculated. Here are my acknowledgments. I'd like to thank John Arco for being my wonderful mentor. I'd also like to thank Matthew Seamack for also being a great mentor, Shannon Kale for also being a great mentor, and Kyle Kingsley for helping out a lot, and Maurice, of course, for helping out when we had questions, and Lori for coordinating FSI, and Karen for helping me out with research papers, and Nick as well for my research paper editor, as well as my advisor. And Adolph Cruz Foundation, without them, I wouldn't have been able to come on this scholarship. And my parents, of course, were pushing me so hard to get me here in the first place. And all the others that were involved in setup and experimentation, so Jessamine, Akshay, Genesee, thank you all so much for helping. Any questions? Charlie.
How would you differentiate the bloodstain with a low angle impact, a lower velocity, versus a bloodstain with a higher angle impact and a greater velocity?
You are going to, but in the width itself is not really going to change. Because the width of high velocity is going to be significantly lower all the time, rather than low velocity is always going to be quite large. And so elongation, however, is going to have the same width, except the length is going to change. So as the length changes and you compare it to the width, that will give you the angle of impact. So mainly width has to do with velocity and length has to do with elongation. So those aren't really going to differentiate too much. Chip.
You said that you can use this type of analysis to determine what, like, the first type, the second type, the third type. How do you do that?
You can use, not this formula specifically, but further research can be done into it. When you swing, you're going to see blood droplets correlating in one line and the blood droplets correlating in another line. So they're not going to be at the same angles directly unless the person is really good. So obviously you're going to see just a line going this way and a line going this way. And you're going to see the different sizes of the cast off. So that's going to be pretty obvious. Sophia?
So what do you do when the blood pattern lines up on, like, the actual circles of blood? What happens when they line up on top of each other? How do you know how to look at that?
Well, when that usually happens, the question was that when blood droplets line up on top of each other, how do you measure them and calculate? So that normally doesn't happen because of the velocity you're swinging back, because those blood droplets are going to fly off at random points. And again, they can be on top of each other, but usually they're not going to be perfectly on top of each other. They're going to be kind of slightly off. This does happen quite a bit. And so you're going to be able to calculate, like if you have two blood droplets like this, you're going to be able to calculate the width of this one and the width of this one fairly easily. So that could be used for an angle again. Harley?
Is your data going to be published or something so that one can see around the country can use this data to kind of like help them know the studies or what studies going on with different solid waste and not
I don't know. Is our research going to be published?
Maybe if we take a little more time and look at the accuracy of what one is come up with first, before just going without the rest of it.
I sure hope that it's further research, because it proved to be very successful in actually calculating the surface size and everything. So I hope it does get published and is able to be used as bloodstain pattern analysis.
So how do you determine the age of each one? How do you determine that this one is close to this one?
Well, in determining that, okay, so the question was, how do you determine the time in which each splatter was given? Mainly, it's usually, when it comes to aging of blood, you're going to see the hardness of it afterwards. And so, in that case, it's going to be hard to differentiate because they're so close together, especially cast off. So you're going to see a slight difference in the hardness and how quickly it has clotted itself and everything like that. As well as you're going to be able to tell, mainly when it comes to aging, it's days after it happens, so you're calculating actually when it happens. But that is a very good question. I can't fully answer it, though. Anybody else? Sophia.
Okay, so you were saying that you recreated your blood off. How did that blood line
study it, but over the course of our experiments, it did have time to actually dry. So we can tell it doesn't dry like normal blood because it's not stuff, it doesn't have the same composition. So it's not going to clot like blood would or harden the same way it does. But it did dry over time. It usually stays pretty moist. Like even after a few days, it'll stay pretty liquidy. Like that sample that we had has been in there for 2 weeks. But it's going to stay mostly liquidy, and you get it on the floor, it's probably going to stay on the floor, liquidy and slippery. But it did compare mostly in the properties of physical properties that we wanted to see right when we did it.